Welcome. It's actually, more in-person guests than I imagined. welcome, and thanks a lot for coming in person. Yeah. Cool. So so today we are very happy that we can eventually meet you guys with this on-site meetup, and we will have 3 talks from 4 speakers today, and they are Ken Chen from Time Plus, and also Ting Wang from Time Plus, and we also have 2 speakers from LinkedIn, Nick and FA. And okay, and so today's agenda would be like this. So we start sharply at 6 o'clock, and with 5 minutes welcome and simple, routine introduction, we're going to start our talks. So the first talk we have would be from Time Plus. It's about Proton. It's a very interesting, project which is trying to do the stream and batch unification. And after that, we will have a talk from LinkedIn, navigating automatic scaling in Pubsub system, and that's going to be delivered by Nick. And afterwards, we have our last talk from FA, talking about how to handle growing Kafka scale at LinkedIn. In case one have question regarding whether this talk will be recorded, yes, and they're going to be recorded and posted on YouTube by LinkedIn Engineering. Also, we will have them, the link available on the Meetup event site once we post it in YouTube. In case there are questions, please feel free to post the questions at any time using Q&A tool in Zoom. So there's a Q&A button on the bottom right side. You can post a question there if you are online. And at the end of each talk, the presenter will answer the questions. And in case you are in person guests here, then you have the privilege to just ask the question by yourself at the end of the talk. Okay. And in case someone want to ask how can I present at this quarterly streams meetup at LinkedIn, feel free to post a message on the meetup site, or you can just reach out to Adam FA, Gary, or me directly using LinkedIn messaging, or you can email us. So I think these slides will also be available online, so you can just find us. Cool. Without any further ado, let's introduce our, the speaker of our first talk today, and that is Ken Chen and Ting Wang. Welcome.
Hey, hello, everyone. Good evening. Yeah, my name is Ting Wang, co-founder and CEO of Time Plus. So my colleague, Ken Chen, is chief architect, co-founder from Time Plus. So today, we really want to introduce a very, like a Beckett. So first of all, thank you for LinkedIn invitation to be here. So give an introduction with very interesting and actually very exciting technology, the product we call the Proton. So I just the highlight just single binary, but it's just we can go through those kind of the background, why we started the product, the project, what kind of use case. And today is also very developer focused. So we really want to deep dive for the technology, see what's going on, what's inside. And also I know a lot of Flink community here. So we're actually a lot of the, something very interesting related to Flink, just we can compare, it's kind of the difference or, very unique things. So, okay. Just quick, I ever give very quick introduction about the team. So Time Plus basically, for me, I previously working for Splunk, almost 60 years there. So Ken is also working for Splunk. It's pretty much like an ex-Splunk guy. So Splunk is for log analytics, so operation analytics. So you can consider that's kind of a subset for the data stream data. So yeah, we have the chief growth officer from the KDB. Probably you guys know the KDB for financial trading, or typical like stream based. So it's a lot of the interesting streaming use case in financial industry. So we also have COO, William Plummer. Yeah, actually he's today. He joined the meeting today. So we pretty much like the 2 years the startup company in Silicon Valley in Santa Clara. So that's the whole team. So I just like back to the background. I think we particularly oversaw this kind of a trend for data streaming. It's kind of like become mainstream. So even for log analytics, we saw a lot of customer consolidate data in the Kafka, Pulsar, a lot of the in there. But how to processing data, analyze data, certainly is a very interesting question. How to enable that? So we go back to our, it's kind of like it's kind of motivation when we go back to the industry here. So we just like okay, how to, from our perspective, what kind of the technology evolvement to tackle this kind of the streaming problem. So we actually pretty much like put the different stage. I think phase one is kind of back to the like 2000. Yeah, it's more likely how handle like a database, how to for the long time the query, how just handle continuous query, how to get it resolved. So it's pretty much like a database technology at that time. And the second generation is just like really need to think like a Flink, a Kafka, those kind of streaming event technology. It's more handled like it's a like out of order event processing, CEP, a lot of technology at that time. It's pretty much for event processing. So we actually put a lot of paper underneath, just like a lot of the academic, is kind of progress innovation there. So we consider like a third generation, just like so the word actually is pretty much when we focus on database, okay, I can do quickly aggregation, large scale data like the aggregation competition. But when we focus on event, we can focus on like an event order, a lot of things, the event specific logic. But for some time, for analytic perspective, when I back to my Splunk career at that time, for a lot of log analytics, you have to do the both. Yeah, you need to know the exactly like a continuous event, but sometimes you have to correlate the historical data. But what about like the one platform, how to solve the problem? So that's why we consider like a time plus just like really, it's kind of the back to fundamental principle, how to handle as one platform. So looking today, I still like the modern data stack still really a lot of different stack, right? So the streaming and also like OLAP or a lot of different things, how to different query language, different semantic. So that's what we're back to very high level motivation. So first of all, it should be very dramatic to reduce the complexity. So how enable the our data team to use the product easily. So I think a lot of it we talk about later. Like a SQL streaming SQL, how to simplify. You don't have to write a bunch of code. Right? The second thing, just like really highlight today, just how enable streaming historic those kind of analytic in the one single platform. So it's just like also with one semantic query language. So I think that's a second, I think most important thing we can talk about today. Hello? Right. Yeah, third item, just like I think a developer always loves the high performance. So how to keep the very, really fast, high performance, like a query time and low latency, and also like EPS, like throughput. I think definitely is our goal. And also how keep the lightweight. It doesn't mean we really want to like single binary, very lightweight. It just can run everywhere, like from the edge side and also for the cloud. So that's something our third, motivation here. So that's actually the encouraging. Yeah, if you guys get a chance, just can try the product. Just like okay, we actually based on the three motivation, the product is really like we use a single binary. So you can use a very simple command like a curve, just like a 300 megabytes. So you can download the library, you can quickly to analyze the data. And the performance is pretty amazing. So it's just like we can give like a single like a millisecond latency, and also the throughput is pretty high. And also, I think you probably can deep dive for some details. The last one, just unify the SQL analytic. So I know the streaming analytic, right? The SQL query is not really finalized the standard. So, but we still try to pilot those kind of semantic, the query language. I think it's really like dramatically to reduce the complexity. And also the couple of use cases, I just quickly like give some, streaming technology, there's a lot of debating part, just like, oh, what kind of the scenario use case? So for our experience, when we have fortunate to walk into a couple of very large scale, the mission critical application with a couple of big companies, first of all, we're going to introduce like real-time trading monitoring. So it's kind of really like, trading is all time is matter, right? The data is always the streaming data. The capital market data, just like, for example, like here, like 3,000 stocks, trading account, they just every second just quickly update to those data. But how to detect those kind of like a trading signal, how to like do like a market making, how to like do like a risk control for this fast pacing the data. So that's very, very typical streaming in the use case. But another just highlight, just like it's not really for streaming pipeline. The risk compliance guy really want to get insight. It's not just like do like ETL job. They have to know, how to analyze, get alerting. For something really like a trading, like alerting, they have to get some, as quick as possible. So that's something really different compared to like traditional pipeline. That's the second case for the like electrical vehicle like security monitoring. So you see it's a very different. It's based on Kafka, but the data is huge. For the edge side, almost like 50 million EPS, and for the second tier, that dramatically say they need to detect some kind of events, aggregate events, almost like 10,000 EPS. So they have to reduce a lot of raw events. And then finally, when the centralized, they need to detect some alerting. So only like just like a very, very like a very minimal, like almost like it's a very small the instant per second. So that's something you have to very hierarchy capability to processing those kind of stream data and raise some different alerting. So that's something very critical case for this kind of we call the edge processing for the vehicle data. So another one, just another very good example, just like it's a network infrastructure monitoring. So it's just like global network provider, just like, okay, based on network data, network flow, I want to detect for example, like a DDoS, like attack. So I think it's a very typical case, but that really want to know what happened as early as possible, close to the router, close to the user. So that needs capability to analyze those data. So that's for example, like here, that for edge side, the EPS like 1 million, like spike EPS almost like 5 million or 7 million EPS. They're just like up and down, but you have the capability to handle that. And there was a latency that they need to extremely fast, like a very, and also the very critical thing is just like they have very environment pretty limit. It's just like a single rack, right? Just like a 6 or 8 core, and also like a 12 gigabyte memory, something like that. It's really like very minimal the resource. You don't have capability. Say I need a huge cluster. So, but as for centralized, they have very pretty good, for clustering environment to handle that. So just go to. So that's our solution. Just like, okay, we can put a very single binary for this edge side. They can connect those data and processing the data as quick as possible. At the same time, they can send to the next one, just centralize to the global SOC center to connect those aggregate data. So that's another like edge case for campus. So that's it. So it's just for the use case. We can maybe talk offline, but I can probably just like try to introduce what's the inside, how to make that happen. So I hand over to Ken.
Yeah, thank you, team. My name is Ken Chen, by the way. Yeah. So next I cover what is Proton. Proton is basically single engine which powers a 10+ product, and And technically what it is. So basically, Proton is a lightweight streaming SQL engine, which is powered by ClickHouse. So basically, we fork ClickHouse code base and start from there. And it tries to resolve one typical problem, which is when real-time data arrives at scale, how can we answer users' inquiry immediately at scale? So it fundamentally is trying to, for the analogy, is basically internally, technically, Proton is basically equal a lightweight solution to Flink, Kafka, and ClickHouse. So folks will basically say, "Are you guys insane?" So because this is a huge monster, three top open source project. Technically, yes, we are insane, and but from product point of view, no, we are not trying to replace Kafka. We are not trying to replace ClickHouse. Yeah, we are trying to combine them to provide a very unified solution, and which is more lightweight and simplification. And regarding the efficiency. So what does that mean? So we have a couple of slides in detail how we tackle this kind of problem. So Proton is basically stands on the giant's shoulder. So for example, there's a lot of good stuff from Kafka. We have learned a lot of stuff from there. And there's a lot of good stuff from Flink. For sure, we have learned some of the techniques from there as well. So ClickHouse for sure. So we are based on ClickHouse, and we are still focusing on streaming processing, streaming analytic, but dedicate the historical query processing to ClickHouse. ClickHouse is very good at historical query processing. So internally, Proton at a high level, it has TCP and HTTP in input format. And in the middle, in this diagram, there's a lot of guts there, and we will deep dive into that. So at a high level, it has stream store, and this is something we built from scratch. We have a historical storage, which is based on ClickHouse. And on that, we have stream append-only stream, we have changelog stream, we have version KB stream, and we have unified processing for sure. And we can query on external stream. For example, we can query on external Kafka topic or Rapanda topic, and we all in different formats, for example, Aerial format, CSV, JSON, you can name it, a lot of them, because we have inherit a lot of legacy regarding the format from the ClickHouse community. And we can query on file logs as well, or different files, CSV file, JSON file, or what kind of different files we can support that. We can also send the data to external ClickHouse because we are based on ClickHouse. So this is a very native integration. If a customer already have a ClickHouse in-house, they do not need to move the data around to different, save another copy of data in Proton. Yeah, so if we dive into the storage a little bit, so when a stream gets created, basically a stream has two parts, the real-time parts and the historic parts at the storage layer. This is the bottom layer in the diagram. So when the data basically get ingested, appended to the stream store. Stream store internally we call distributed replicated native log. So some of the it is append only. Some of the fundamental technology is basically borrowed from Kafka. Kafka is append only, right? But the replication is our replication is not is using a different distributed algorithm, which is multi-route. And also when the data append to the replicated native log, when it is committed, in the meanwhile, in the background, we have different threads basically consume the data, committed data in the native log, and write the data in batch to the historic data store. So, and from the user's perspective, they do not need to worry about the internal details. So, for example, when user issue a query, and internally we can try to, what's the data? Where's the data I need to look at? Some of the data may be in the historical store, and some of the data may be in the streaming store. And internally we can glue them together. Because do not need to worry about how we glue them together. And later we'll deep dive into how we can, when a query travel through historic data store to stream data store, and how we handle that. So if we dive into the streaming store, which is native log, this is fundamentally a replicated write-ahead log. and we borrow a lot of idea from Kafka as well. So which is powered by multi-raft consensus. So one thing I like to mention is that on the file disk we have built different reverted index. For example, on the left, on the right in this diagram, we have segment file. And segment file we have built a inverted index for sequence number to file offset and sequence or timestamp, event timestamp, append timestamp to sequence number. So basically, we build the inverted index for logical timestamp, which is sequence number, and we also build inverted index for the logic time, physical timestamp for event timestamp and also for append timestamp. This is basically very useful for you if we like to rewind the stream, and we can do fast lookup where I can, for example, if you seek to rewind the stream to a specific timestamp, we can use this inverted index to fast look at where the file we need to look at. That will be a little bit more overwhelming. So in each of the log segment, which we have the log entry. In the log entry, we have a specific file format or data format. So probably I do not have much time to deep dive into each of them, but at a very high level, we have for the data payload and metadata payload, metadata part, the data part. The data part is columnized. Is columnized in columnar format. Columnar format has basically the very good very good nature, which is enable vectorized streaming processing. So vectorized stream processing is super powerful. If we have a batch, for example, if we have 100 events there, if we can use this modern CPU SIMD to do the aggregation, that would be way more fast. And the other benefit is basically the serialization benefit is the cost is the cost is super small. So since that our in-memory representation and on disk file representation keep basically the same. So you can basically load the data from the on disk and then deserialize it to in-memory. That will be really fast. And on the in the data part is basically the some of the database technology, which is projection pushdown and the product is pushdown. Projection pushdown is like I have 10 columns, but I like to only select 2 columns from them. I do not need to worry about the other 8 columns. We can fill a lot of data very soon at the storage layer. Product pushdown is like when we have a timestamp, but we like to query a timestamp, but the timestamp does not meet that the condition. We can prove the log entry that we can fill out the whole log entry very quick. That will be performance will be really good. And the other metadata like towards the schema evolution, data format evolution. Probably we do not have time to cover that use cases here. So except the storage layer, we also like to tackle the query processing. So we just talk about the storage layer, about the stream store, historic data store, and the log format. But query is basically run on top of that, and we have revised the stream query processing because SQL is not stream SQL is not standardized. We have tried. The community basically, we are one of them. Try to standardize streaming SQL, but it turns out it's super complex. So far, we do not have a standard. But the syntax, the streaming syntax is basically we borrow a lot of idea from the one SQL to rule all. That paper, that scientific paper is from Google and written by Tyler Arkido. That paper basically influenced a lot of the SQL usage and also data SQL processing semantic we have based on that paper. And also regarding this SQL processing, we are also there are other two scientific papers which impact our foundation of the foundation query processing, which is Borealis and also Aurora. And the team just showed that a couple of slides, people. But in general, we can do SQL. We can do streaming query processing in the SQL. We can do table query processing in the SQL. We can combine them together. We can do pure table query processing. We can do pure streaming query processing. We can unify them in one SQL as well. So since that we are based on ClickHouse code base, and each of the queries basically constructed to an execution plan. So it's just a DAG. This DAG is super important because it's impact our how to do the state checkpointing. So this is basically some everybody do this stuff. Flink does this stuff. Almost every streaming vendor basically need to do some kind of state checkpointing. So the DAG basically we have got a lot of good idea from Flink as well. So state checkpointing is like similar idea. We have basically periodically emit the very special watermark, which is a checkpointing watermark, and that the watermark basically flow through the whole DAG. And for there are two stateful operator in the DAG which need to persist the data. One is the aggregation, and then another is join. Once everything persistent to the query store state store file system, and we can basically finish one round of checkpointing. Yeah, this kind of mechanism is basically from very similar to Flink, and as I said, so we have Proton is basically stand on the giant's shoulders. We borrow a lot of good ideas from there. So since that Proton unifies streaming and historical query processing. So when a query travels through from a historic data store to stream data store, basically we do not want data duplication. We do not want data gap. So how do we do that? Basically, every time we commit the data, consume the data from native log and commit the data to a historic data store, basically we commit the sequence ID as well. And when for example, if you have a query, I like to rewind the data, backfill the data 1 day ago, and we basically will pick one day historic data from the historic data store, and then connect the data with real-time data, which is from stream store. So we are using the sequence ID, lots of sequence ID to connect these two pieces together. From any user point of view, it is a very consistent view about the query processing. So historic data store, we can also use the historic data store for the streaming data enrichment lookup, and also we have a lot of use cases like troubleshooting. So streaming is really good at real-time alerting or monitoring. So for example, if there's some CPU high usage, but if you like to do deep dive why the CPU is high, you still need to dig into the raw logs or raw events. So that for this kind of use case, basically historic data store can try me. User can do ad hoc query against the historic data store. So another use case is basically we have a lot of data in historic data store. You like to do real-time comparison about a window in historic data store, maybe 10 months back, and using 10 months back window to real-time compare the window right now. So this is another use cases. There are quite a lot of other possibility. If we control the storage. Lastly, basically we have SQL is not the perfect to handle some of the use cases like state machine processing, which is very stateful, right? You have one input, and you see some events. You basically jump to another state. And then you have a final state. It's really hard to express this kind of process this kind of use cases by using pure SQL. So we have some use cases user like to do state machine based processing. So we extend this Proton to support the JavaScript, user-defined function and user-defined aggregation function. So basically, user can create a user aggregation function, do all kinds of streaming processing. Yeah, and you do not need deployment because our Proton basically embedded V8 engine, JavaScript engine there. So finally, I'd like to do a comparison regarding the user experience between Proton and Flink. Right. So on the left side is Proton SQL. On the right side is Flink SQL. So for example, this use case is based from one of our community user. Basically, he like to do as of join, but his latency is super strict. As of join is basically I like to find the closest match. Closest match. For example, I have join condition, but I like to we have another join condition, but I like to do, for example, timestamp. The timestamp need to be nanosecond precision, and I like to do that. We have a equal match. That's fine, but there may be a lot of candidates. In all of the matched candidates, I like to find the best one. This is fundamentally how the out of join does. So this is a financial use case is that he has a very strict latency, join latency, and also throughput. So on the left side we have Proton SQL. On the right side we have Flink SQL. So let's see how they correlate each other, or how they compare to each other. So on the they can, the first of all, they can create a stream, external stream, basically to point to the topic. On the left side and right side, basically similar stuff, pointing to a broker 1992 and topic events. And then both of them create a view. So for example, I like, this is the second, create a sync topic. I like to write the data to this topic, because we have source, we have sync. And then in the middle, we have create a different view, filled out the data. We like to basically, these two are basically the same. And also create another view. We like to, this is, the first view is basically the order book. The second view is basically the peak in financial service. And lastly, in Flink, they need to create another view, which is basically filled out the using the partition by, order by, to get the latest data, latest order book. And in TimePlus, we do not need that. This is the meet. This is the final case. Final case is basically like to join the view, join like to a streaming join. Basically, we have left streaming, we have right streaming. They like to join together and like to do, first of all, do the equal join, which is basically the tick instrument and BBL instrument. And then we like to do a as of join like sequence. So the sequence is the best match. For this case specifically, the community user basically try Flink out and also Proton out. We have 3x better latency. We have 3x better latency and also 2x memory usage efficiency. And to the best of my knowledge, it looks like Flink does not support nanoseconds timestamp. This is from the community user. Basically, this is what he said, and he needs quite a lot of different workarounds. Yeah. So lastly, I'd like to do a quick demo, which is another use case from community users. So like stream aggregation 1 billion events with 130 million unique IP predicts. And so he tried a lot of web vendors, but most of them does not work because of the memory efficiency problem. So because 130 million unique IP fix is a lot, and it quite basically different solution below all the solution, basically below the memory. Let me do real quick. Oh, I need to log on. 1 second. So since that, I can do a curl command to download the single binary, because everything is one single binary.
Can you actually zoom in a little bit? I think the font is too small. I think.
Oh yeah, font is small. Oh yeah. So I just download the binary and nothing here, and I can just launch it up, and then import. using Proton client to attach the server and create a screen. And then I can run select. Basically, I create a random screen and so basically, it's randomly generated a lot of unique IPs, and which is basically 130 million unique IPs, and we are processing 1 billion events, and it's already done. So this is 134 rows, and it's processed 1 billion events in 15 seconds. Let me run this again because it's real quick. And see the usage here. The usage is basically 8 GB and 9 GB. And yeah, it's done. It's already almost 9 GB, and in 15 minutes we can get that done. Yeah, this is all I have today. Thank you so much. So by the way, last any question? Lastly, basically, Proton is open source. Yeah, if you like to try, give it a try, give it a spin. Yeah, because it's super easy. Just like curl command to install the Proton in your local directory and spin it up, and it can do streaming query processing and historical query processing in one single binary. Thank you.
Okay, thanks, Ken. So I think we have a question online. So FA, do you want to bring that question up?
Yeah, so we have 2 questions. The first question is from Shin. The question is wondering what the advantages with respect to the local embedded engine approach versus uploading events to remote services / databases. Is latency the primary consideration?
Yeah, that's a really good one. So it's basically the number one, absolutely the performance. Number 2 is basically consistency. So if you have different storage, it's really hard to guarantee the consistent. This is a well-known challenge in community. For example, you have storage in Kafka, you have downstream in Iceberg or different storage. It's really hard to coordinate them together. So if we build everything in one single binary, so it is still lightweight, and you can coordinate all of the storage stuff. Performance for sure. This is another well-known problem because different product has different protocol, different data format. You need to convert from one data format to another data format, and then in the middle, you still have your own data format. The data format conversion, deserialization, serialization is super inefficient. And since that we built everything in one single binary, so we basically control the data format in the stream store and the historical data store. Basically, they are pretty the same. Yeah, performance and the consistency, they are the major facts, major advantage. And another one is the simplification. We in Time Plus we're pushing really hard to simplify our product. Everything should be single binary. Even in our cluster deployment, we do not leverage any kind of external system like etcd or Zookeeper. We leverage nothing. So everything is in one binary. Thank you.
Thank you, Ken. There's one more question from remote audience. Is there a benchmark comparison with other platform under the same test scenario?
Yeah, so we have some very initial test scenario. If you folks are interested, you can log on our Time Plus website. We have some, but we do not have any kind of benchmarking stuff. We do not have that. Like we have some of the specific use cases. For example, for the as of join these specific use cases, I think we can beat most of the vendor there, but systematically benchmark, we do not have that yet. Not yet so far.
Thanks, Ken. There's one more question, but we are at time, so maybe we can take this asynchronously while we move to the next speaker.
Thank you.
Thank
Yeah.
you.
Single binary based solution. In mostly all other distributed computing framework, they are JVM based.
Yeah.
So what is the motivation like to move out from that JVM based distributed computing to C++ based computation?
Yeah.
And how do you manage
Mhm.
a kind of because I think Flink has a scheduler, and scheduler has a role to play how tasks could be distributed across different machines in the different JVM for parallel processing. How do you handle it actually in Proton?
Yeah, that's a really good. This is a really good one. So we first of all, so regarding the language, first of all we stood on the shoulder of giants. So we basically fork the ClickHouse code base and start from there. ClickHouse is super. If you folks know ClickHouse is super good at very super efficient about the C++ implementation. And from our perspective, so in this new era, so hardware is basically advanced so much. So for example, a NVMe SSD can handle, I don't know, maybe hundred thousands of ILPS, right? So the best one, Samsung, I think is hundreds thousands ILPS, and the throughput is basically 20, maybe 30 gigabyte per second. For this kind of monster, it's really hard to using the existing technology or existing software. The software stack is basically lagging so behind, and also operating system is basically progressing as well. So, for example, in the latest Linux system, they have the new modern IO ring, this kind of operating system code. This is basically pushing the IO and to a new frontier. So we think we can do better. We can in this new year we can do better by using leveraging existing C++, and language stuff is also evolving. Like C++ 23, the standard is out, and in time perspective, we adopted the latest C++ standard always. And we upgrade our compiler, LLVM, Clang, basically always using the latest C++ language in time pass as well. So regarding the consensus, yes, or distributed query processing in Flink, our community user also raised this kind of question. We tackle properly in a different way. So for example, we can schedule in Proton cluster, we can schedule the query to any kind of node or any node in the cluster. Any node can talk to different nodes to get the data and do the query processing on that node. So so far we do not schedule one query. We do not schedule one query into different nodes in the cluster, because it turns out that our single instance of Proton can handle hundreds of millions events per second aggregated. So this is super powerful enough. And also, if we schedule one query to different nodes in the Proton cluster and do another aggregation on the initiated node, the performance is actually downgraded a lot. And we do not have a customer which has that much of load so far. Yeah. Thank you. Any question? Probably I'm running out of time. Yeah.
That's okay. Oh, okay.
Okay,
Thanks.
thank you.
All right. Thanks a lot, Ken. Yeah. All right. Thanks, Ken, again for the fantastic talk. And we're going to have our second speaker, which is Nick from LinkedIn, to talk about how to navigate automatic scaling in Pubsub systems. Welcome, Nick. Yeah.
All right, thank you. All right, hi, I'm Nick. I'm a site reliability engineer here at LinkedIn. LinkedIn operates a truly massive amount of Kafka here. It's some very large clusters and also many clusters. So today I'm going to talk about how we have these clusters auto-scale in response to the things that require them to. So first I'm going to talk about capacity dynamics, the things that make us want to grow or shrink these clusters. Next, I'm going to spend some time talking about cruise control. Hopefully you've heard me talk about that before, but if not, I'll give you a quick overview. I'm going to spend some time talking about how do we automatically add and remove brokers from the cluster. Not necessarily like fully automatic, but just, we need to add something. What does that process look like? I'm going to talk about, okay, how do we merge all these things together to get to fully automatic? And then some lessons we've learned along the way. Okay, so the first capacity driver, this one should be pretty obvious. LinkedIn has been very successful. That is good. It's also meant that the needs on Kafka have grown substantially. We recently hit 1 billion members. That's obviously amazing. The demands on Kafka have grown, both as our user base has grown, but also as our employee base has grown. As people join the company, they want to add new, maybe ML models, recommendations, anything like that. Even if the user base was constant, the demand on Kafka would grow. User base is not constant though. Definitely getting bigger. Traffic is coming, launching new stuff all the time. So most obvious reason why we need to grow our Kafka clusters. Just talk about that. Hardware failures is one of the reasons why hosts need to come out. Especially Kafka, storage system. We used to run these kind of very large hard drive servers where it'd be one host with like 12 or something disks. That many hard drives in one place, they're going to fail a lot. We got to get them out of the cluster, get them repaired, put them back in, take them out, maybe put a new host in. It could be, again, drive failures, but we also have less timely things like maybe there's a power supply imbalance. We have seen things where like memory has been corrupted, right? That can be very dangerous, especially on a storage system. This in particular was a pretty big pain point for us on the SRE team, just operating this. Part of that reason is we had to deal with all these by hand. So we had a case where our Kafka clusters were growing, and then we needed to scale the number of people that worked on the clusters literally with that, because we would have these failures all the time, and then we would need to manually go and remove these hosts. Super painful. One of the reasons we're talking about this today. One of the other reasons why we find ourselves actually turning over the entire cluster is this concept of a hardware refresh. Hardware evolves, even if hosts are still working totally fine, maybe something newer is coming out. So I talked about how we have these hard drives, again, we'd have like 12. These would be these like really big servers, like physically large inside the data center. They'd get hot, they would tend to fail a lot, relatively painful to deal with. But obviously it worked. But technology evolved. We got these NVMe cards. So that's the thing on the right. These, actually storage-wise, they're actually denser in terms of just like the physical space that the card takes up versus the storage that it has. But it's also very small. You can put 2 of these in a server. The actual host itself will be a fourth of the size of what we used to have in the old one. So both in terms of just way improved reliability, but also just the people at data center were very, very happy when we stopped making them wheel around these super heavy racks and start using the much smaller ones on a more kind of standard server where we just slotted in these 2 big NVMe cards. But in order to go from one to the other, we had to refresh all of our hosts. This was very time consuming, and if we didn't have the tools I'm going to talk about today, we would have needed a much larger team, and they would have been much, much less happy if they were doing it. So hardware refreshes, these happened. This was a pretty major one, but we do these all the time as things evolve. Okay, so the way we used to do this before, we had all these tools. If we wanted to do something as simple as just drain a Kafka host, if you run Kafka and you're not using the tools I'm going to talk about today, you are unfortunately very familiar with this command. You would do something to take this JSON file that you've manually crafted, and then that would move all of your Kafka partitions around. This is terrible for a lot of reasons. First you're like updating some config file to like shuffle things. You wish it was just a command, but also you're making a ton of decisions that you just really don't want to. Like, let's say I don't want my broker number 2. I then need to manually decide where all these partitions are going, right? All these replicas are going. I don't want to make that decision. I just want to say, okay, get everything off this host, put it in a good place. I'm not trying to manually assign stuff. So you both have to make a lot of decisions you don't want to. have to do it by hand. It's some bash script that wraps some like Java call. This is not the way that we like to do things. Okay, so fortunately, there's this wonderful tool called Cruise Control. Could absolutely give a talk on this. FA, who's going to speak next, has given many talks on this. I'm not going to talk about it today, but I'm just going to give a quick overview of what this does and why this has truly been a miracle for us in terms of just operating the massive number of Kafka hosts that we have. So Cruise Control has a lot of components. I'm just going to talk through some of them. The first one I want to point out is that Cruise Control, it's not just a read-only system. It's not something that just like makes proposals on what you should do. Cruise Control actually directly acts on the Kafka cluster. So it has a bunch of logic in place. It decides, what it thinks the state of the world should be. But either because a human tells it to, or it decides to, it will then move data around inside your Kafka cluster. So I just want to point out, like, this is a system that actually does something for sure. The next thing I want to point out is that Cruise Control has this load monitor. So it's continuously getting metrics from your Kafka cluster, and then it's building its own cluster model. So it is looking at the current state of the world. It is querying all of our brokers. It takes some time to build this model. It doesn't like save it and then reload it when it loads. Like when it starts up, it needs to build this. And, it's noting that for us, we have some really big ones. It'll take hours sometimes to build this model. So we need to be really conscious of when we're restarting it. But it has this model and then it's loaded into the parts to come. The analyzer is a set of goals. The Cruise Control has this concept of soft and hard goals. So a soft goal is something that it would like to be true, like a distribution. It would like to have replicas distributed relatively evenly across hosts. It would like it if the CPU is balanced. These are things that it prefers to have. However, there's also a concept of a hard goal, and this will come up again later, where it will refuse to push a host past a certain amount of CPU. All these things are configurable, but we'll say we do not want Cruise Control to ever put load on a host if it goes over 75% CPU usage. And Cruise Control actually refused to act on the cluster if it is unable to satisfy that. So we have a set of hard goals. We do this for like rack diversification. We don't want to make sure that too many replicas are in a single rack. So we have stuff for that, CPU. We never want to push the disk over, like if we're going to move data on and then run out of disk space. I don't know if anybody here has ever had a Kafka server run out of disk space, but not easy to recover from. So as this analyzer, it is able to take that cluster model, look at the changes it wants to do, and then see how it's going to impact those goals. And then it uses those goals to do the optimization. And then the final part, which is truly wonderful for us, is it will look for anomalies either in terms of those goals. So if something is drifting outside of an acceptable range, it's great. It will actually recognize it. And then if you configure so, begin to rebalance the cluster. So it'll just automatically do this, where it'll say, okay, you're running out of disk space on this host, move the data somewhere else. Don't even need a person. Also, it'll watch the cluster and say, okay, a host has failed, the drive has failed. Let's drain it. Let's get it out of there. So Cruise Control, truly a really important piece of this whole puzzle. But actually adding and removing hosts. So everything I just talked about is moving data around, like draining a host or even loading a host. We do this. Cruise Control will actually load a host once we add something, but we need to actually add and remove the host from the Kafka cluster. This is something, LinkedIn, we run our own data centers. We have our own custom infrastructure deployment stack. We need some logic to actually go ahead and add and remove these hosts. And this Cruise Control is open source. Our infrastructure is certainly not all open source. So we on the SRE team had to build something to add and remove these hosts. The system that we use for this is called Kakashi. This was built by somebody called Akash in our team. He said it is named after some anime character. I have other suspicions on why he named it that. I think he was just sneaking his name in there. But we use a workflow engine called Camunda. It works well. I'm not going to say it's particularly amazing, but the important thing is it provides us with this workflow that we use to add and remove things. There's a lot going on here, so just to kind of break it down into parts. The first thing that we do is we just keep our ticket. So as we are adding or removing a host from the cluster, we just keep a record inside our ticketing system. This is really valuable. I'll talk more about this later. The next is this maintenance mode that we added to. Maintenance mode is a way to say, okay, when we are adding new replicas, like things are getting moved around, don't add them to this host. Like if we're doing this remove workflow, we certainly don't want to be adding more things on this host as we're trying to get it out. The next part is draining Kafka replicas. this is a cruise control call. Super easy. Cruise control does this for us. Thank you. Then the next part, that's all the LinkedIn infrastructure specific stuff. We issue commands to our deployment stack. It actually stops Kafka. This all happens after we've already drained it. So we know we're good to go. We don't need to do a bunch of shuffling. Disable maintenance mode, close Jira. The remove is pretty easy. Adding is more complicated. You can see more boxes. This has been a reoccurring theme in my career. Is it's a lot easier to turn things off than turn them back on again. However, the concepts are still kind of block-based here. A lot of it's really similar, but we have this lock at the beginning. So we have a pool of spare hosts. Again, we run our own infrastructure. We don't have some cloud. So if we want a new host that we want to use, we need to select it with this workflow and then start Kafka on it. But we can be running 20 of these workflows at once. So we need to make sure that multiple of them are not grabbing the same host. So we get this lock, select the host. Once we have a host that we want to start on, we can let that lock go and make sure that we're linked with that host. We then start Kafka on it, and then start something called Kmon. This is a monitoring agent that we use here at LinkedIn. The whole alerting and monitoring stack is built on top of Kafka at LinkedIn. That's great for everybody else, not so great for us, because if Kafka goes down, then we lose all that signal. So we had to build our own agent and our own alerting pipeline, and that could be a talk of its own. But we need to start that when we start Kafka, of course, and then close that record. And then we actually have it set up so cruise control is querying this agent as well to get some of this information. Okay, so that's adds and removes. Cruise control is automatically draining hosts when they fail. We're close, but it's not fully automatic. Even when we had this all in place, the tool that we use we have like a UI that we use to do a lot of this management. When the on-calls at the end of the day would go and they would click, okay, this host has failed, remove it. They would just click a button to remove it. It would all kind of happen, but it's still just, a kind of stupid part of our job where we were just going ahead and clicking things. We would also get this signal from cruise control. I talked about hard goals before. Once cruise control recognizes that maybe there's just too much data in the cluster. We see this all the time, traffic ramps, new users, things like that. If the data has grown the cluster such that cruise control can't balance it, it's like, I'm going to push a host over whatever the threshold we set, let's say 80%. If we're going to go over 80%, cruise control will refuse to do anything, give us a signal, and then we were going in and adding hosts as a response. So cruise control is telling us, hey, you need to grow the cluster, but it wasn't growing it. We were still growing it. Again, we're close, but we're not there. Fortunately, cruise control actually has something in place to do this. So this is the thing I would really encourage you to kind of take away from this if you're using cruise control but not using this, is cruise control has this concept of a provisioner. So it has this cluster model, it has all these detectors, it is very aware of how big it thinks your cluster should be. It'll actually call a function that you define that says, hey, I want to add to your cluster, I want to remove from your cluster. So it will say, maybe you need this many disks, you can figure it. Maybe you want this many racks. It'll also say, this is how we use it. Please add 5 brokers. But remember that we did a hardware refresh. Our clusters are often kind of a mixture of hardware at a time. It doesn't really make sense to say add 5 brokers because it's okay, it's a big one, it's a small one, what type. So what cruise control will actually do is it'll say add 5 that look just like this other one in the cluster. So it'll give you a reference broker and then say add 5 more of these. This is kind of the trick that hooks everything together. So again, if you're using cruise control but not using this provisioner, I really encourage you to, because this pieces it all together. Okay, so I guess kind of before I move on though, I'll just comment, now that we have this, that is really it. So we're already using cruise control to balance things. We built this system to add and remove hosts. This pieced it all together. This actually worked surprisingly well for a very long time. So let me talk about the stuff that we did right. As we did this, and I'll talk about some things we learned along the way. The first is integrating with Jira worked out really well for us. We have a record of the more than 10,000 of these operations we've done so far. It's especially me, I do a lot of infrastructure planning and stuff like that. It's really good to see where are hosts going. When I order hosts, they go in some spare pool and then get pulled into the cluster. Where are they going? Hopefully why. This kind of helps piece it together. Even before we were on full auto, this is really good because I could see, okay, our spare pool got much smaller as of yesterday. Why? And I could see, okay, somebody accidentally added an extra 0 when they added hosts. got to go chase that down. But the record is really good. It lets us attach it if there's an incident. We could say, oop, we had this outage. It was because we removed too many hosts. Here's the record, all the tickets. Just having this audit log, especially integrated with our kind of key tooling, makes it really quick to check stuff. Integrating with Jira worked out really well. So just tracking cluster operations is kind of the theme here. The second thing is safety. So when you have a system that is especially removing, but also adding, you want to make sure that it's not taking away things that are going to push you over some capacity limit, or even much more importantly, make it so you have insufficient replicas. If you run Kafka, you're well aware that if your replica count goes below a certain number that you configure, they'll go read only. This is a streaming system. Like, people are producing data. One of the reasons using Kafka is because they don't want to store it. They just want to dump it into Kafka and figure out what to do with it later. If your replica is read only, like, that is a major outage. That's a very key focus of our team, is to make sure that doesn't happen. So we need to have some checks in place to make sure that doesn't happen. Fortunately, cruise control has one. So cruise control, like I said, it has its hard goals. If you try and do any action, in this case, call remove broker, and you're crossing those thresholds, cruise control will just refuse to do it. And you can't even say, like, as long as it's evaluating this goal, you can't force cruise control to do it. The second thing that we have in our open source branch of Kafka is this concept of a controlled shutdown. So that safe to shutdown call, what that is doing is that is actually checking, okay, if this Kafka broker turns off right now, is it going to put any of these replicas in read only? So what we actually, like, if you send a sig term to this Kafka process, it'll do this check. It'll say, I'm not shutting down. Like, you can't make me, because I'm going to send a replica into read only. Now, of course, you can make it if you really want to, but this check is also just a kind of another layer where even if something went wrong and we're about to, like, induce an outage accidentally, either through our automation or human asking it to, this safety check definitely saved us more than once. Okay. Now I'm going to get into some lessons learned. So this is this year, unfortunately. There's been a lot of growth in our Kafka clusters. Usually it's pretty steady. So you can see up to that spike, things tend to grow at kind of a steady rate. Some steps, people launch stuff, but overall pretty reasonable. We make it easy for people to use Kafka here at LinkedIn. This is good, but it also means that if people come along and then substantially ramp out of nowhere, we will get alerts. We'll be like, hey, we're running out of disk. Like, what's going on? We need to go to cluster. However, we had just launched the full auto, where we're automatically growing and scaling these systems. So it just grew. Like, it just ate every single spare host we had. We didn't even notice until we looked at our spare pool and we're like, wait, where did all hosts go? Like, it actually just, we had all these alerts in place for when things didn't work. We're an SRE team. We're always on top of this sort of thing. But when it worked too well, we didn't even notice. So when you find yourself, like, automatically scaling these systems, it's natural to want to check when it's not working, but it's also really important to check when it's working too well. That's absolutely what we had here. And clawing hosts back is very painful, and this is what we had to do. The second thing is, even if you are automatically draining these hosts, if the people in the data center are not aware of it, they're going to keep asking you as part of the old process, hey, can you drain this host? Hey, we found this failure, can you remove it? We were like, every single one of these messages, and these were all me, were situations where we had already drained this host. I mean, maybe it wasn't even like running our system anymore, but because this was happening all automatically, they didn't know. So they're just used, they're like in Texas, just messaging us saying like, hey, trying to take this host offline, but they didn't know that it already was. So you need to basically be aware of the full life cycle of the hardware and make sure that's integrated with them. Once we basically hooked into their tooling, all these went away and it was like truly automatic. We have host failures now and we don't even know about it unless something goes wrong. Yeah. Okay, so let me just give a quick summary. The first thing that I will say is if you are still adding and removing brokers by hand, get away from that and produce an API. If you're running on a cloud, they have one. Hopefully that does most of it for you. Hopefully you have some sort of image that you spin up and that takes care of it. If you don't though, even without the cruise control logic, it's still really good to have the API. The next thing, I talked about that provisioner before. That interface is great. That is what hooks it all together. Again, if you're using cruise control and not using that provisioner, that's what you should get your hands on. And then lastly, you still got to keep an eye on things, even if a human's not involved. We were aware of this, but we didn't think of all the cases, especially one where it was very successful. So automatic scaling is great, but you still need to have some kind of check-in. We've actually incorporated it where every single week we're just like reviewing capacity numbers just for like 30 seconds, but just enough where we catch things if things are going wrong. Okay, that's it. Any questions? Yeah. Oh.
How big the Kafka cluster is in LinkedIn right now? And the scenarios where you have to remove some of the brokers. And yeah, definitely it's actually continuously growing. But in which scenario you need to actually remove the brokers from the cluster?
Okay, so the first question was how big are our clusters? I don't know if I can actually give the official like max size, but I'll say hundreds. So we're not like thousands yet. Like we certainly have more than thousands of Kafka brokers, but in individual cluster it's hundreds. The second question, so when are we removing hosts? So a lot of it is just hardware failures. We also, especially this past year, have had a lot of like efficiency efforts where we've gone through, we've said, okay, do we need as much data as we're saving? Kafka is largely a retention-based system. Some of these are large data sets. We're like, do we really need 2 weeks of this? And like the answer is no, we need like 3 days. So we went through and we did a whole bunch of those efforts. That was good. We saved a tremendous amount of money, saved us as we're doing our hardware planning, like we saved a bunch. But as a result, the Kafka cluster is way oversized. So then cruise control actually says, hey, I think you're too big. Right now, we actually have that turned off. We are still kind of doing the removes by hand because these events don't happen very often. So then once we did, we then used all the tooling to say, okay, remove this many hosts. We did the calculations, and then also we're happy that these safeties were in place where if there's something wrong with our calculations, cruise control would refuse to do it. Okay. Yeah, good question.
Thanks. Any other questions? Okay. So if there's no more questions, then thanks, Nick. All right, with that, let's welcome our last speaker who is online, FA. So FA is the engineering manager managing the Kafka team on LinkedIn. So, okay, FA, you'll have the stage.
All right, thanks for the introduction, Beckett. Today I'm going to talk about a topic where Nick briefly mentioned that at LinkedIn, Kafka is growing rapidly. And as the birthplace of Kafka, we have been the longest user of the system. So there has been organic growth, there has been growth due to new use cases using Kafka. So today I'm going to talk about how we handle this growing scale of Kafka at LinkedIn. And what do I mean by handling the growing scale of Kafka? The agenda of the talk consists of 5 parts. First, I will give a brief background on Kafka, our data streaming platform. And then I will delve into the 3 pieces of the talk. The first part is going to be about how to manage this growing scale of Kafka. And then I will move into how we handle unused metadata, which has been growing over time. And finally, I will talk about how we identify the scale limits and what scale limits that we look into. And then I will wrap it up with a summary. So without further ado, let's begin with a brief background on Kafka. So Kafka is our data streaming platform. It provides a high throughput with low latency, persistent storage of partitioned data on brokers, and total ordering within each partition. Some of the key concepts are people store their data in the topics. These topics are partitions, and these partitions are replicated and distributed over brokers. In this example, we have 3 brokers in a Kafka cluster with a replica of partition 1 of blue topic that is shown at the bottom. And we have another red topic with multiple partitions, a single partition with multiple replicas distributed. We also have leaders and followers. There's replication, it's primary backup replication. Followers fetch data from the leaders, and they are leaders and followers reside on different brokers in the cluster. So on the client side, we have producers. Producers generate data to a selected set of leaders for the topics that they're producing to. And consumers retrieve the data from these topics to process them in their application logic. If brokers fail, which they do fail frequently, then the leaders are going to be unavailable for a brief period of time. In those cases, Kafka automatically handles the leadership transfer by choosing the next preferred replica in the replica list to transfer the leadership, so that producers and consumers can still use the topic for produce and consume operations. So next, let's talk about what scale we are talking about at LinkedIn. What is our growing Kafka scale? When we look at the number of brokers in our clusters, we have large Kafka clusters for various use cases, including for tracking purposes, metrics. We are using large clusters. And one of our large cluster, for example, is in the order of 400 machines, 400 hosts running 400 brokers. We also have clusters with a lot of replicas. When I talk about replicas, it is the partition count multiplied by the replication factor, which can be 3 or 4, depending on the cluster. And we have around 4.4 million, over 4.4 million replicas in our stable clusters. Actually, in Nick's talk, he has shown that there has been cases where we have seen even higher number of replicas in our clusters, but this is more like a stable situation. We have about 4.4 million replicas in those clusters, big clusters. And we also have a lot of traffic into our topics. So we have around 42 trillion messages that are flowing into the topics in our Kafka clusters. These messages are sent to around 500,000 topics on around 10,000 brokers. And this scale is growing since the time that I prepared this slide deck to today. We have now larger numbers on all 3 fronts. Then how do we handle growing Kafka scale, and what does it mean to handle the growing Kafka scale at LinkedIn? So this is a multifaceted challenge. When we talk about handling the scale and scalability, we want to achieve a target throughput, latency, and availability. And the way we define those targets are based on SLOs at LinkedIn. And this is happening in the presence of increasing traffic due to either organic growth or new use cases onboarding to Kafka, metadata pressure due to creation of new topics or partition count increases, and operational requirements. So we also don't want to compromise the key features offered by Kafka. We don't want to change anything about its distributed nature, durability, or fault-tolerant design. With that, let's look into what do we mean by managing Kafka clusters and why do we need those. First of all, we have large heterogeneous clusters. We have a large number of clusters and large clusters by themselves. And by heterogeneity, what I mean is we have machines with different disk space. We have machines with different number of cores. We have brokers with different NIC sizes, some having a better network capacity, some having lower network capacity. So there are changes. We have frequent hardware failures, and OS upgrades are also frequent. Some of these requirements are happening because there could be a freshness requirements for your operating system. So you may need to do this OS upgrades rather frequently. And cluster expansion and reduction also happen frequently. So we need to add brokers to our clusters as they get larger, and we may want to remove brokers from the cluster to save cost or shift the resources to other clusters where there might be more need for them. To achieve that, we have cruise control. The vision of cruise control, the high-level goal of it is to provide auto execution of actions to satisfy SLO requirements while saving time, effort, and costs. And it does this by providing admin operations for cluster maintenance, enables anomaly detection with self-healing, and also offers real-time monitoring of Kafka clusters. If we look into these admin operations, they're basically rebalancing the cluster to shift the load to make sure that our operational requirements are satisfied, adding, removing brokers, demoting brokers, which means removing the leadership from the selected set of brokers and transferring them to the other brokers in the cluster, fixing the offline replicas, which might be offline due to either broker failure or disk failure, preferred leader election, which moves the leadership of each partition to their most preferred replica, and partition count increase of topics. Partition count decrease at this point is not supported by Kafka. Now, the interesting one here is the rebalance of the cluster. Let's take a closer look at that. If you look at the rebalancing requirements, we see hard goals and soft goals. So for the hard goals, these are the ones that must be satisfied. So we can't operate our cluster without satisfying these goals. And these are things like ensuring rack-aware distribution. This could also be if you have some fault domain requirements, the distribution of that could be a hard goal for you. Never exceeding a certain threshold of broker capacity. Let's say that I set a limit of 70% capacity for selected resource. I can't run the cluster with utilization above that. Ensuring a minimum per broker leader count for selected topics. This, for example, could be relevant if you're using Kafka monitoring, which is another open source project of LinkedIn, in order to properly measure the availability of your cluster, of your brokers. You may want to have a certain number of leaders from selected topics from Kafka monitoring topics in your brokers. Enforcing operational requirements such as maximum replica count per broker could be another hard goal. And when we look at the soft goal, the difference is that they're best effort. So they may not be necessarily satisfied 100%, but to the extent when it is possible, cruise control tries to satisfy these goals as much as it can. These include goals like ensuring balanced disk, CPU, and network utilization over brokers, minimizing the clustering of partitions from each topic on a few brokers, ensuring balanced replica and leadership distribution over brokers, and handling potential outbound network load. The potential outbound network load here refers to if a subset of brokers die, the remaining brokers will not fail due to excessive outbound network load on them. So we talked about rebalancing. So next interesting topic that I want to talk about is about self-healing. So self-healing refers to an automated action to fix an identified anomaly. And when we talk about anomalies, there are a bunch of them. So goal violation is an anomaly. So any of the hard goal or soft goal violation can be an anomaly in the system that needs a rebalance to fix that. Broker or disk failure is an anomaly. So if a broker fails, we are losing the redundancy in the cluster. So let's say that I have a replication factor 3, it is no longer true. So I have 2 replicas if a broker fails. And I want to fix that. Similarly, if I'm using JBOD deployment, and if I lose the disk, I want to bring the redundancy back to its original value. So this will trigger an offline replica fix by moving replicas around in the cluster. Slow brokers are the brokers that are still up and running, but they're not performing as well as I expect them to perform. So they have some gray failures. And for such brokers, there's also self-healing action to demote them and remove them from the cluster. There could be misconfigured topics, which might be bad replication factor. So somebody might set the replication factor to lower than it should be in this cluster with the way that it's configured with min in sync replicas config. I may want to have a certain gap between min in sync replicas and the replication factor for the partitions of that topic. So in those cases, cruise control can again detect And if self-healing is enabled for it, it can fix the replication factor anomalies. And there's also maintenance event anomalies, which based on created maintenance events, cruise control can take actions to fix the cluster. The third part of the cruise control features is the real-time monitor. So using real-time monitoring, the operators of the cluster can examine relevant states of the cluster. So this includes examining the replica leader and load distribution over the brokers, identifying under-replicated, under-min-ASR and offline partitions, or checking the health of brokers, disks, and user tasks. So this is the high-level architecture of cruise control. So Nick in his talk also mentioned a bit about this. So the key components here are the monitor, executor, anomaly detector, and analyzer, which is the brain of the system that makes decisions based on the cluster model that it gets from the monitor. And then it passes a plan to executor, which then executes this in the Kafka cluster in a throttled fashion so that it will not overwhelm the cluster, but at the same time, it will move it, continuously move it to a better state, an ideal state. So I also want to share some numbers on how cruise control helped us and how it continuously helps us. For example, for automated daily actions that cruise control generates, we have around 900 of those to fix anomalies every day. The balancedness here refers to the state at which the cluster satisfies the requirements that we set. So how well it satisfies its hard goals and soft goals. And based on this, 90% of our clusters at LinkedIn have a balanced score of over 80 out of 100. And the gray failures that we have refers to brokers that are up and running, but they're not really performing well due to some issues, underlying issues. Some of these issues are detected by other systems that we have at LinkedIn. So if there's a hardware failure, sometimes they might be detected. But sometimes these systems may miss those issues. And in those cases, cruise control looks at the performance of the broker based on comparison to its peers and comparison to its own historical values, and then identifies if there's an abnormality in a selected set of brokers. And in those cases, they're slow, it alerts us. So in this figure, for example, there was a slow broker which was showing significantly higher flash time. And then we remove this from the cluster to fix this performance anomaly. With SSDs, such issues are observed less, but they still happen. So the next part of the talk, we talked about the cluster management. Now, I want to briefly talk about unused metadata. So what do we mean by unused metadata? So I mentioned that Kafka was, it emerged at LinkedIn and it was open sourced by LinkedIn and contributed to the community. So it has been running at LinkedIn for a long time. And so sometimes we have some topics that may not really be used in the cluster. And these topics generate a metadata pressure due to redundant fetches also, where let's say that I have a replica that has a follower. The follower continuously fetches from the leader regardless of whether the leader receives traffic or not. So there is a CPU utilization impact of this fetch. If a controller has a failure, if we need to do a deployment, for example, where a new version of Kafka is deployed, then the process of new controller being initialized and taking over the controllership requires it to do some initialization based on the number of topics in the cluster, number of partitions in the cluster. And this process itself also takes a long time. So this is another adverse effect of having too much metadata in the cluster. And we did some analysis to see to what extent we are affected by these unused topics in our clusters. And we have seen that the number of unused topics in our clusters was significant. So the red part of the graph here shows the fraction of unused topics in each cluster. And in some cases, you can see that maybe there were 2,000, over 2,000 topics that were unused in some clusters. So why does it happen? It happens potentially because of changing business needs. People may no longer need those topics. They may not use those topics. New schema adoption could be another reason, where people have some backwards incompatible schema, and as a result, they stop using that topic and start using a new topic. Topic versioning. So sometimes there are use cases where people create one topic with one version number, bump up the version number, create another topic, and keep going like this, which leaves a lot of unused topics behind. And there are also some leftovers due to testing. For example, there's my test topic 2, my test topic 3 that can go on like this, and that leaves a garbage behind that is continuously growing if it's left unattended. And how do we address this? We use a service called Topic GC. So this service continuously detects and deletes unused topics at LinkedIn. And there are 3 parts that I want to emphasize. It notifies topic owners before the deletion. So it doesn't do this quietly. It lets the topic owners know. It ensures no data loss. I'll talk more about how it achieves that. And it also handles external service dependencies. So I'll also talk a bit more about that, but at a high level, it means regardless of whether the topic is detected as used or not, based on the traffic, it might still need to exist due to some external dependencies, which need to be handled first before the topic can be deleted. So this is the workflow of Topic GC. If you look at the top left corner, each box represents a state. So this is a state machine, and the arrows here represents the transitions between these states, these actions. And if a topic is considered as used, then it will not be deleted. If a topic is unused, which requires satisfying the criteria that we set for topics to be detected as unused, then it will send a notification. So at LinkedIn, this is an email to topic owners, but it can be configured as another form of notification, can be tied to Slack, Teams, or something else. And then there is after notification, there is a block of write access if still there is no use or no requirement to keep the topic. And then the mirroring is disabled, which stops sending the data to other clusters if it was being mirrored. And then the topics are deleted. So let's delve into a bit about detecting the usage. So what do we mean by a topic being used or unused? So an unused topic is empty. So it needs to have 0 bytes on disk. It has no incoming or outgoing traffic. It has no access in the past X days, where X is configurable. So let's say it's past 90 days. And it was not created again within the past X days, another configurable parameter. If a topic satisfies these, then it's an unused topic. So I also want to share a specific impact at a selected pipeline. So by pipeline, what I mean is multiple clusters for the same use case. It could be, let's say, tracking metrics or something else that I mentioned earlier. So in this specific case, we had around 30% of the topics identified as unused in this pipeline. So In particular, we had over 2,000 topics received or served no traffic and had no data on it. So they were unused. The CPU overhead that was generated by these topics was, after they were eliminated, it was compared before and after. And the CPU overhead per broker on average was about 7.5%. And this was mainly due to the replica fetchers. So replica fetchers were still continuously trying to look for data on the leader node. And they were finding no data, but they were still running this process of fetching the data. So eliminating this 2,000 topics saved around 7.5% CPU overhead per broker. And the metadata request delay here was, this is the P99. And the delay was reduced around 40% after this cleanup. And this was due to no more delays, stale responses, and timeouts with the elimination of these 2,000 plus topics in the pipeline. And finally, the last piece that I will talk about is identifying scale limits. So identifying scale limits refers to answering the questions of what are the dimensions of growth? When will we hit the scale limits? And does my cluster need more storage, higher CPU speed, or a faster network? So how do I make these decisions in an informed manner rather than randomly picking the best machine that I think the best machine? So to do that, we do bottleneck analysis. And here, the bottleneck analysis refers to identifying the constraints and inefficiencies on growing Kafka scale. So we identify dimensions of growth, we do performance testing, and then finally, we do reality check on those. So let's look into the first one, the dimensions of growth. So in our analysis, we identified that there are some dimensions that are critical to track. And these are tracked not just per broker, but also, depending on the context, it could be tracked in the cluster as well. So some of them affect in the broker level, some of them have effect on the cluster level as a whole. And we look into incoming and outgoing bytes into brokers and cluster, incoming message rates, produce consume request rates, and also topic count, partition count, and replica count, and connection and broker count. So we know that these dimensions, as they grow, they will have impact on our SLOs, the thing that we value. And we want to see where the limit is. And to do that, we do performance testing. And when we do performance testing, we focus on two parts. We do load testing and we do stress testing for Kafka. And the question we try to answer with load testing is, does the system meet our expectations for this load that we expect to have? And with the stress testing, what we try to do is, if I continue increasing my load, what is the failure point? At what point it will stop satisfying my requirements? And to be able to run these tests, we use a tool that we have built called Pubsub Stressor. So this is a service for testing the performance with synthetic traffic that we generate. And the synthetic traffic that we generate can be based on our realistic traffic in selected clusters. And then based on the estimates, we can follow this pattern of traffic with, let's say, high fan-outs with multiple consumers of the same data. And then we can multiply this with excessive load on the cluster to create the level of load we want to have in the cluster. And it runs producers, consumers in separate threads, allows us to set custom traffic pattern, size, and type. And it scales horizontally. So we can have more and more instances of Pubsub Stressor to generate more load into the cluster. And finally, based on the results that we get, we do the reality check. So, and when we look into the analysis of the results that we get, we consider the impact of site traffic on Kafka clusters. So not every Kafka cluster has a direct correlation between the site traffic. Some are strongly correlated with site traffic, some are weakly correlated. So if we expect the site traffic to grow to some extent, and we need to also ensure that the clusters which are expected to be correlated, strongly correlated with the site traffic, need to handle the resulting load on their clusters. So that's why it's important to know the impact of site traffic on Kafka clusters. And we also do these estimation, extrapolation, and forecasting based on the input that we get from multiple parts. So, for example, we look at the historical usage in the cluster, historical byte rates coming in, coming out, going out in the cluster. And based on that, we come up with some estimations on what its future load is going to be. We also consider the new use cases that are ramping up on the cluster. And so they all go into this estimation, extrapolation, and forecasting. And then we consider the options that we have. We look into horizontal versus vertical scaling. Can we just add more brokers, or do we need hardware upgrades? So do we need to have machines with stronger CPU or faster disks? We also consider whether we want to keep the cluster monolithic, one big cluster that keeps growing, or do we want to split the cluster? It's possible that for the same use case, I can have multiple physical clusters, and I can onboard my new users to my new physical cluster. And also we look into client versus server-side improvements. Do we need to change something in the code? Do we need to change something in the configurations to ensure the efficient, proper use of the cluster resources? With that, so we looked into how we handle the growing Kafka scale at LinkedIn, and we discussed how we manage Kafka clusters at LinkedIn using cruise control, how we handle the unused metadata with topic GC, and how we identify scale limits, and what we do with the identified scale limits. And with that, I will take questions if there are any. Thanks.
Okay, thanks, Efe. So I guess you can see the online questions by yourself, right?
Yes. I think currently, yeah, we don't have online questions. If there are any questions in the room, I can take those.
Any question? Cool. It looks like there's one.
How do you find out who owns the topic?
Oh, so at LinkedIn, we have the resource ownership is controlled by a separate system. So each topic has to have an owner, and using that system, we can identify the topic owner.
Any more questions?
I see one online question from Sachin Tate. How long is the typical process to bring a topic down once identified? I suspect this question is about if a topic is identified as unused, how long does it take to remove it? How long does it take to delete it from the cluster? So yes, Sachin clarified it's unused topics. So the process is dependent on the parameters that we feed into it. So if we look into this workflow, there is a user wait period where, so if the topic is identified as unused, based on our criteria, it has no access in the past X days, there's 0 bytes in it, there's no incoming or outgoing traffic, was not created within the past X days. Let's say X is 90. So within the past 3 months, it was not accessed. So it was identified as unused. On top of that, there's a notification that goes to the users, the owners of the topic. And then there's a grace period. This is also configurable. Let's say that that's another 10 days. So now we are at 100 days of unused topic. And this wait is also done and there's still no use. The topic is still not accessed by anyone, either by consumers or producers, it's not accessed. Then the next step is to block the write access. So after the write access is blocked, it moves into disabling mirroring. So mirroring is, by the way, is transferring the streaming the data from one cluster to another using, at LinkedIn we are using Brooklyn. Brooklyn is another open source project. It's available on GitHub. This is also disabled, and then the topic is deleted. So it may take, depending on this example configuration, in this case, 100 days. All right.
Sorry, this you described, you said it has no access in the last X days. How do you find that out?
Yeah. So there is a topic that we have in each cluster where it tracks information about whether a topic is accessed or not. So we have access information for the resource. And then if that access information shows that there is no access to the topic, and then in the state machine, it goes into unused state.
Okay. Any other questions? Okay, no more questions on site.
Thank you.
All right, thanks everyone for coming. Hopefully we will see you next time as well. All right, and we will have the next one in 3 months. So we have this quarterly streams meetup. All right, thank you again for coming.